Hey everyone. Today we're going to continue with our lesson on electric circuits. Today we're going to focus on parallel circuits. Previously we had looked at series circuits, which only allow one path for current to flow. And a parallel circuit is going to provide more than one path for current to flow. So a parallel circuit is a circuit in which elements are connected between 2 points with one of the two ends of each component connected to each point. That's kind of a lot to think about and a lot to comprehend there. I think it makes a little more sense once you see what it looks like. So I'm going to draw this parallel circuit with 3 resistors, a battery, and our connecting wires. Those are the 3 things we're going to need for a simple circuit. And I'm going to use the schematics that we can find on page 4 of our reference table. I'm going to start with a battery which contains multiple cells. And a parallel circuit is going to have multiple paths for current to flow. That's our resistor. That's a poor connecting line. We'll connect this over. We'll call this R1. I'm going to do a couple more. We'll call this resistor R2, D2, and we'll put another one in here. We'll call this one R3. So this is a simple parallel circuit. You can see that current can flow from the battery and go down this path, it can come down and go down this path, or it can continue further down and go down the last branch of the circuit. So in this case, there's 3 different paths, or 3 different branches for current to flow. And this is the main difference between a parallel and a series circuit. The series circuit, if we just break apart one of these branches and look maybe at this first part here, if we look just at this circuit, we have everything here that we need for a simple circuit. A source of potential difference, connecting wires, and a circuit element, a resistor. So that one portion could be considered a series, but with these other 2 sections added on there, this whole circuit becomes a parallel circuit because now, from the source of potential difference, our battery, there are multiple paths, multiple branches for the current to flow. And because of this, our current, voltage, and resistance, equivalent resistance, is treated differently than it is in a series circuit. Now, as far as current goes, to find current going through each one of these resistors at any point in the circuit, we're going to add up. Let me change my writing utensil here. We're going to add up the current from each branch. The current flowing through each branch will give us the total current in the circuit, the current leaving the battery. And this is and so on, however many we were to have. So this is the sum of all currents to each resistor. The voltage and current are kind of flipped from a series to a parallel circuit. Now the voltage is going to be the same at every branch as it is from the source, depending on how many branches we were to have. So the potential difference I'm going to abbreviate this, remains the same to each resistor. So whatever the voltage is coming out of our battery, it's going to equal the voltage 2, voltage 1, or voltage 3 entering either of these branches of this circuit. Now the equivalent resistance, this is going to be the most challenging part of parallel circuits and determining any of these values. Now, equivalent resistance, we actually call this 1 over Req, where the equivalent resistance is represented in the denominator of this fraction. And that's equal to 1 over the resistance of the first resistor, plus 1 over the resistance of the second, plus 1 over the resistance of the third, and so on. Now this has to be set up as a fraction. And I'll show you some examples of that momentarily. Now this is really the basis of what you need to know to handle parallel circuits, are these three equations. Knowing that current can flow or can take different paths through the circuit. And we'll do an example here in a second. But this information is applied in a lot of different ways to a lot of different scenarios. And I think this is one of the harder parts about dealing with electric circuits. That this little bit of information is applied in a lot of different ways. So we'll apply this to the example here. We have three resistors of 6 ohms, 8 ohms, and 24 ohms connected in parallel to an applied potential difference of 24 volts. So I'm just going to define some things here. R1 is 6 ohms, R2 is 8 ohms, and R3 is 24 ohms. You can put these in any order that you want, it doesn't really matter. And they're connected in parallel. We're going to make sure that we see that there. It's connected in parallel to an applied potential difference of 24 volts. So our voltage here is 24 volts. We don't know our total current. We don't know the current through each resistor. Because I1, I2, and I3 are going to add up to the total current leaving that 24 volt source. So this is what we know so far. And I've set this up in a circuit using the PhET Simulator circuit construction kit. And I haven't adjusted any of these values yet, but if we click on these, we can adjust these. I'm going to bring this up to, what do you say, 24 volts. And each resistor here, we have one at 6, 8, and 24. We'll keep this set up a similar way here. And this one will go to 24. And now we have our circuit. So you can see a couple things here. And I think these are great for dealing with circuits, and for any of the questions you have involving circuits, you can build them on here. And as I'm going to show you in a second, we can use the voltmeter and the ammeter to check and see what this is. And not that this is a way to do these types of problems all the time, but it's a great way to learn and to check what you're doing. So we can change this to the schematic view where we have what I had drawn here on the notes, 3 resistors and their battery, connecting wires. And one thing we'll point out is that these electrons here, we have electron flow. We can switch this and do conventional flow, which is the reverse, but we use electron flow in the scope of this class. And if you look at the flow of electrons, it's very different in different spots of the circuit. It's really slow over here. It's really fast right here. It's kind of a little bit faster here compared to here. And even just coming down each branch, this branch looks a lot slower than this branch, which might make a little bit of sense. There's a lot of resistance here, kind of like a big beaver dam. And there's a small beaver dam here. So the current's flowing a little faster through here than it is flowing through here because there's more resistance. Now we can pull out our voltmeter. We can check on both sides of the battery here. What's our voltage? Okay, well it is in fact 24 volts. And point this out, it says it's a minus 24 volts. And that's simply because these leads are installed backwards. If we flip them around, we get a voltage of 24 volts. So that was just reading it in the reverse direction. I'm going to keep this away for now. We're going to check the values here current in a second. But first, we're going to find the equivalent resistance. Now, in a series circuit, we simply just added these up. 6, 8, 24 gets us 38 ohms. If this were a series circuit and these were connected end to end, we'd have a total equivalent resistance of 38 ohms. But in a parallel circuit, this is not the case. In a parallel circuit, this is a similar kind of circuit that you'd find in your home, where you might have your circuit box here, and you have some wires that might come down to a light in your bedroom, to an outlet in the room, and then maybe to, I don't know, another light. Maybe you got a light, overhead light, and you got a light next to your bed, and an outlet. But there's different paths that you can flow. And the reason why we can tell that this is different, let's say you have the first two here we'll call lights, and the third one here we'll call it television. Okay? Now, the way a parallel circuit works, if we shut off one of the lights, the TV still stays on. If these are connected in series, if we shut off one of the lights, the TV wouldn't work or the other light wouldn't work. So this is how we can use power in the home without having to have everything on at once. But what this does is it affects our equivalent resistance. So every time we add a branch here, this is going to affect the overall current that's coming from the source. And if we produce too much current in a particular circuit, the flow of moving electrons creates a lot of heat. And therefore, depending on how much we're drawing, could potentially melt circuit components, heat up, cause a fire. So what we do is we put circuit breakers in the home. And this is used as a safety mechanism. So for example, if you have a microwave that runs on, let's say, 12 amps, and you plug in your toaster at the same time, which draws, let's say, 10 amps. The total there is 22 amps. Now, depending on the circuit in the home, the outlets, the wires, and the circuit breaker itself is meant for a specific amperage. And in general, most circuits in the home are 15 amps. So if you draw more than 15 amps, a circuit breaker opens, and you essentially blow the breaker, blow a fuse, and you can no longer run anything that's on that circuit until you go down and you reset it. So generally, microwaves and large current drawing items are put on their own circuit, so they're not blowing breakers all the time. And in your home, if you are blowing breakers all the time, it's probably due to one, having too many large items on the same circuit, or it could be with how the circuit was wired originally or adjusted over time. Now we'll see here with equivalent resistance, the more resistors or more branches that we add, the lower our equivalent resistance becomes, which will ultimately increase the amount of current flowing through our circuit. So let's see. To find equivalent resistance, we know it's 1 over the equivalent resistance, and that's equal to 1 over R1 plus 1 over R2 plus 1 over R3. And we're going to have to draw on some of your past experience with adding fractions. So we end up with 1 over 6 ohms plus 1 over 8 ohms plus 1 over 24 ohms. Those are the three resistors that we had in our circuit. So now 1 over our equivalent resistance becomes those three added together. So we find a common denominator, say 24. 6 goes into 24 4 times. So we have 4 over 24 plus 3 over 24 plus 1 over 24. And this gives us a total of 8 over 24 ohms. Now we have to make sure when we set these equal to each other, this is going to be equal to 1 over Req. This top number here this has to be a 1 in order for this to work correctly. So to change that, we'll divide 24 by 8 to make that a 1. And that'll give us a 1 over 3, which is equal to 1 over Req. So Req, equal to the number in our denominator there, would be 3 ohms. So as long as we make that numerator a 1, the bottom number here will be our equivalent resistance. And we can't really check that here. We can't measure resistance in here. We could calculate it like we just did using our 3 resistors. But the total comes out to about 3 ohms. Or excuse me. Yeah, 3 ohms. Now that equivalent resistance is less than the resistor in any branch. So the total resistance of the circuit is less than the 6, 8, or 24 ohms of either of those branches. And the more branches we add, the lower that equivalent resistance becomes. It's like constantly opening up smaller little creeks to a bigger river to try and get past the dam. Overall, your equivalent resistance will decrease, current will increase, and this is why in a parallel circuit, circuit breakers are required, because the current, the flow moving through each of our wires and components in the circuit can get so hot that they can melt and cause a fire. Calculate the potential difference across each resistor. Well, we know that the voltage from the source is 24 volts, and we know that in a parallel circuit, the potential difference is the same at every branch of the circuit. So the 24 volts will remain the same. So V1 equals 24 volts, V2 equals 24 volts, and V3 equals 24 volts. I want to check that. Now we did this before. We checked both sides of our, I flip those again. 24 volts there, so let's check across each resistor. Get it on there, 24 volts, and again we can move this to any spot here in the circuit across any of these resistors, and we're going to have 24 volts. Okay, doesn't matter where you put these, the voltage, the potential difference is the same anywhere in the circuit. Now the current, we know that the sums of the current at every branch equals the total current from the source. Now we have to actually find the current at each branch. And we're going to use the voltage and the resistance, because we're looking for the current through each resistor here. So we're going to use the resistance and the voltage through each branch to find the current through that resistor. So the current through the first branch here, we're going to use the voltage through here, and we're going to use the 6 ohms. Well, using Ohm's law, that would be V1 over R1, or 24 volts over 6 ohms. This gives us a current through the first branch of 4 amps. Now the current through the second branch, we're doing the same way. It's the voltage through the second part of the branch, which is still going to be the same, and the resistance of R2. So this remains the same, 24 volts. And the resistor R2 was 8 ohms. And this comes out to 3 amps. The current flowing through I3 will be the voltage and the resistance of R3. Still the same here, 24 volts. And this last one here, what did you say it was 24 ohms? Is 24 ohms. And this comes out to 1 amp. So now the total current here is the sum of all of the currents, which is a total of 8 amps. So we have the current flowing through each resistor. So this 1 amp was I3. This is I2. And this is I1. Let's check that. We'll use the ammeter here, which has to be connected in series. We'll talk about that in our next lesson. So we said the current flowing through the first part of the branch here was 4 amps. We checked that there. We put that in any part of the circuit here. We have a current of 4 amps. Okay? And that's on any part of the branch through the resistor. The second one we said was 3 amps. We'll double check that. Yep, it's 3 amps through here. Okay, and the last we said was 1 amp. And we do have 1 amp through this part of the circuit. Now if we put this coming out of the battery, we can check the amperage. We can check that as it goes down the line. We said the total was 8 amps. So we should have 8 amps coming out of the battery. And we do. Now if we check the other side, we also have 8 amps. Who would have thunk it? Now if we move this past this first branch, which had 4 amps coming down it, how many amps would we see right in between here? If you guessed 4, you were right. So the 4 amps that went down this branch were lost from the total 8. And we're left with 4 moving through here. So this is the flow of 8 amps. This is the flow of 4 amps. And this is even less here. We know that 3 amps goes down here. So this would be a flow of 1 amp. So we see a flow of 1 amp through here. Here we see a flow of 3 amps. Even down here as well. You can check that. I guess it would be, yeah. The 3 plus the 1 here, we'd get 4. We got 3 here, plus the 1 adds up to 4 here. And then the other 4 coming down here, we'd get a total of 8. So the current's different in each branch. And once we lose some current to a branch, there's less moving down to the rest of the remaining branches. We'll do extensive practice with each of these, and I'll give you guys another lesson here on how to use meters and how to calculate power and conservation of charge in a circuit. Make sure you guys write down any questions that you have, and make sure you ask them when you get a chance. Have a great day.